Good morning. In today's class, we'll see some few small topics by definition, followed by shear force and bending moment topic. Just a definition and the small amount of explanation. Hardness is the ability of a material to resist deformation, which is determined by a standard test where the surface resistance to indentation is measured. The most commonly used hardness tests are defined by the shape or type of indent, the size, and the amount of load applied. Strength. Strength measures how much stress can be applied to an element before it deforms permanently or fractures. Ductility is a mechanical property where a solid material stretches under tensile strain. If ductile, a material may be stretched into a wire. Or in other words, ductility is the ability of a material to be drawn or plastically deformed without fracture. It is therefore an indication of how soft or malleable the material is. Examples of ductile materials like gold, silver, copper, etc. Brittleness describes the property of a material that fractures when subjected to stress, but has a little tendency to deform before rupture. Brittle materials are characterized by little deformation, poor capacity to resist impact and vibration of load, high compressive strength, and low tensile strength. Examples: bone, cast iron, ceramic, and concrete for brittle materials. Static load. It is nothing but a load which does not change in magnitude or position with respect to time. Dynamic loads which change in either shape, position, or direction with respect to time. The sudden load acting on any structural member is defined as impact load. What is beam? Okay, what is beam? A beam is a structural element that primarily resists loads applied laterally to the beam's axis and causing the beam to bend, thus producing deflection. Okay, a beam is nothing but an horizontal structural member on which the load will be applied perpendicular to the longitudinal axis of the beam, so that the beam bends and produces deflection. Now we are going to see what is statically determinate and indeterminate beams. Okay, and these are the static equilibrium equations. For example, we are having 6 static equilibrium equations. Sigma fx is equal to 0, sigma fy is equal to 0, sigma fz is equal to 0, which is nothing but, for example, if I take sigma fx is equal to 0, is nothing but algebraic summation of all forces acting along x direction is equal to 0. That's the meaning of that. Forces acting, for example, right side is positive, left side is negative. This is a sign convention. Similarly, the algebraic summation of all forces acting in y direction is 0. Upward force is positive, downward force is negative. Then similarly, sigma f z forces, that is the algebraic summation of all the forces acting along the z direction, is 0. And if you write the equation, static equilibrium equation with respect to the moment, sigma mx is equal to 0. That is, you are taking moment about x-axis, okay, about x-axis. So the algebraic sum of the force moments of all the forces about x-axis is equal to 0. Clockwise positive, anti-clockwise negative. This is an convention we have to remember. Similarly, sigma my is equal to 0. The algebraic sum of the moments of all the forces about y-axis is equal to 0. Sigma mz is equal to 0. The algebraic summation of all the moments, algebraic summation of the moments of all the forces about z-axis is equal to 0. Okay, so these are the, for 3D case, we are having 6 static equilibrium equations. But in solid mechanics or the strength of material, we'll be using sigma fx is equal to 0, sigma fy is equal to 0, sigma mz is equal to 0. Okay, sigma mz is equal to 0, which is nothing but, if you just imagine that this diagram is on a paper having x-axis and y-axis, so z-axis will be perpendicular to this plane or a paper. That's why it is written moment about z-axis. Okay. If you're taking moment about a means sigma m z suffix a, which is nothing but the moment about z-axis only, but we are taking the moment with respect to a reference point a. Okay. So sigma fx is equal to 0. So right side force is positive, left hand side force is negative. Sigma fy is equal to 0. Upside force is positive, downside force is negative. Okay. Sigma m z is equal to 0 or sigma m is equal to 0. Sometimes it would be written as sigma ma is equal to 0. Clockwise positive is clockwise moment is positive, anti-clockwise moment is negative. Now here the figure it is shown, this beam is, we can call it as a simply supported beam or freely supported beam. Okay, so where RA and RB are the unknown support reactions, okay, and these are the 3 static equilibrium equations which are used to determine the unknown support reactions. Okay, unknown support reactions. So these are the 3 static equilibrium equations. You can see here number 3. Okay, so here let R suffix A, RA be the number of unknown support reactions. Now in this case, simply supported beam, RA and RB are the 2 unknown support reactions. Okay, unknown support reactions. So if RA is less than or equal to 3, the beam is referred to as statically determinate beam. Okay, so RA is nothing but number of unknowns in a given beam, and 3 is nothing but number of static equilibrium equations. So if RA is less than or equal to 3 means the beam is referred to as statically determinate beam. Okay, coming to the next beam, this is also simply supported beam. So we are having the hinge support as well as the roller support. Roller support, one vertical reaction that is normal to the support, and hinge support, one vertical so unknown support reaction and one horizontal unknown support reaction. Total we are having 3 unknowns. Again, RA is equal to 3, that is 3 means the number of static equilibrium equations that we are having here. So this is also called as a statically determinate beam. Okay, so number of unknowns 2, number of unknowns 3. So RA is nothing but number of unknowns. Okay, so we call this as a 3 static equilibrium equations. Now let us go to the next cantilever beam. Okay, cantilever beam where one end is fixed, other end is free. So here one vertical reaction, one horizontal reaction, one one moment is acting. So 3 unknown reactions. Okay, so again these 3 unknowns is equal to the 3, that is 3 static equilibrium equations. So I can call the cantilever beam as a statically determinate beam. Okay, statically determinate beam. Come over here, a cantilever, but at the free end is supported by a roller support. Okay, if the free end is supported by a roller support means this is called as a proper cantilever beam. So here 3 unknowns, here one more unknown, 4 unknowns. Okay, now static equilibrium equation is 3, but number of unknowns is 4. So RA is greater than 3 means it is referred to as statically indeterminate beam. It is referred to as statically indeterminate beam. So now you can see this is a continuous beam, a beam having more than 2 supports. We call it as a continuous beam. So RA, RB, RC, 3 unknown support reactions and 1 support moment. So 3 plus 1, 4 unknowns. So here fixed end beams. So here three unknowns. So here three unknowns. Okay. So we call it as we are having six unknowns here. We call it as statically indeterminate beams. So here it's a fixed continuous beam. Okay. So three unknowns here RB, as well as we are having the intermediate support moment. So 3 plus 3, 6, 7, 8 unknowns. So which is called as statically indeterminate beam. So what are the types of load that we are going to see generally in applied solid mechanics for plotting the shear force and bending moment diagram? So we call this as a point load, okay, represented by a point, okay, point load. P is a point load acting at some distance. It could act anywhere along the length of the beam. Point load or a concentrated load. We call this as a UDL, uniformly distributed load. Uniformly distributed load. Okay, so sometimes it would be represented as like this also. Okay, in the textbooks. Okay, you can see like this. Okay, so like this also it would be represented. Okay, so UDL, uniformly distributed load, and this is a triangular load. Okay, triangular load or uniformly varying load. Okay, maximum at one end and other end it would be zero. So triangular load or uniformly varying load. Okay, so trapezoidal. So here if you could see, this is a combination of UDL and UVL. Okay, if you just try to draw a line here like this, for example, okay, if I try to draw a line like this, okay, so this becomes the UDL, uniformly distributed load, and this becomes, okay, this becomes the UVL, uniformly varying load. So it's a combination of UDL and UVL, which is called as trapezoidally distributed load. Okay, trapezoidally distributed load. So next is the point moment, okay, or we can call it as a couple. Okay, it could act anywhere along the length of the beam. Okay, point moment or a couple. We can call it as a couple. Okay. Types of supports that we are going to see in solid mechanics with respect to the shear force and bending moment diagrams. This we call it as a roller support, where you will have only one support reaction like this. Only one unknown support reaction. Okay, so now suppose if this roller is at some angle, for example, okay, like this. Okay, so roller is inclined at some angle. So your support reactions, remember in roller it should be always normal to the support. This is your unknown support reactions. Okay, so this is your beam, for example. Okay, so this is the angle acting, whatever be the angle, theta, for example. Okay. So next, this is the hinge support, where you will have one vertical and one horizontal. Okay, you have here, for example, if R is the unknown support reaction at point A, for example, and I call this as a vertical, so RAV, for example. Now, to come to this, for a horizontal one, R, okay, A, at A, it is acting horizontally. Okay, in some textbooks it would have written like this also, reaction, horizontal reaction at A. Okay, so here vertical reaction at A. So like this also you can write. Okay, it is understood. So cantilever beam is nothing but to show the fixed support. Okay, this is the fixed end of a cantilever beam. As I told you earlier, you will have one vertical and you will have one vertical, for example, like this. Okay, one horizontal and one moment like this. Okay, so this direction of this couple or a moment depends upon the direction of the load acting on the beam. Okay, so you must remember that you are having three unknowns at the fixed end of a cantilever beam, and you have only one unknown at the roller support, and you have only two unknowns at the hinged support. So this is called as hinged support. Sometimes this is called as a pinned, P-I-N-N-E, the pinned support, or okay, and this is simply supported. Sometimes this is called as a freely supported, fixed end, sometimes built-in end, sometimes clamped ends. Okay, so those terms we need to keep in our mind. Okay, now we are going to see, for example, I told you by definition a beam is nothing but an horizontal structural member, okay, which is resting on any type of support, okay. So it can be classified or called as a simply supported beam, or fixed beam, or cantilever beam, or overhanging beam, or a continuous beam, whatever you let it be, any type of beam. And if the beam is loaded with a point load, or a uniformly distributed load, or uniformly varying load, or a trapezoidally varying load, whatever it is, or if a beam is subjected to a couple, we need to study if these loads are acting on such beams, what would happen to the beam? That is, if the loads are acting on a beam, that is, the loads are acting, for example, perpendicular to the longitudinal axis of the beam will bend. The beam will be subjected to bending, okay, which produces a bending moment or a bending stress or a deflection, whatever it is. So along the span of the beam or along the length of the beam, shear force and bending moments are set up. That is, shear force values changes along the length of the beam, and bending moment value also changes along the length of the beam depending on the magnitude and the type of load acting on your beam. So how to plot all those diagrams? How to plot the shear force diagram? How to plot the bending moment diagram? That we are going to see in this chapter. So by definition, what is shear force? So the algebraic sum of the vertical forces at any section of a beam to the right or left of the section is known as shear force, which is represented by SF, capital letter. The algebraic sum of the moments of all the forces acting to the right or left of the section is known as bending moment, represented by shortly BM, bending moment. So a shear force diagram is one which shows its variation along the span or length of the beam. Bending moment diagram, BMD, which also shows the variation of the bending moment along the length of the beam. Sign conventions. Okay, always in engineering, if we want to calculate any numerical values, we need to follow certain sign conventions, different sign conventions followed by different authors, but we have only two sign conventions, that is signs like plus and minus. Okay, so if the beam bends like this, if a beam bends like this, for example, okay, originally when it is, I mean, before loading, the beam will be horizontal. Once when it is loaded, the beam bends like this. At the top surface, you could see concavity. At the bottom, convexity. We call this as a positive bending moment. Okay, or we can call this as a beam is sagging. Okay, sagging bending moment. Okay, you could see here the clockwise, post clockwise, here anti-clockwise, the moments are acting. then only the beam will cause to bend. Okay, bend. So this is a section, suppose if you're taking. Okay, so this is the left side of the section, this is the right side of the section. So left side of the section, clockwise movements positive, and the right side of the moment, anti-clockwise movements are positive. Okay, so this we need to keep in our mind. Okay, suppose, so this is for sagging bending moment. Okay, if you just change the direction or the magnitude of the loads acting on a beam, sometimes there is a possibility of hogging, Hogging, hogging. So we call this as a hogging bending moment or negative bending moment. Okay, on the top convexity, at the bottom it is concavity. Okay, so you can see here this section. Okay, so here it is anti-clockwise, here it is clockwise. So left side anti-clockwise negative, we call this as a negative, and clockwise is, so right side clockwise is, this is anti-clockwise negative, clockwise is negative on the right hand side. Okay, so we call this as a negative bending moment, we call this as a positive bending moment. That we need to keep in mind while writing the bending moment equations. So we have taken a beam. So we are taking some section. You can take anywhere the section, any type of load will act. Okay. Just for the sake of example, I have taken some section here, acting at a distance x from the left hand left hand support A, for example. Okay. So now, for example, at the left hand side, okay, at the left hand side, okay, shear force acting upward is positive. If the shear force is acting downward is negative. Okay, in some books they would follow upward is negative and downward is positive. Okay, it's your wish, but you have to follow some standard sign conventions. Okay, so before start solving the problem, you can write these assumptions. Okay, from the left hand side, if you're trying to write the equations for shear force or bending moment, from left hand side of the section of the beam, upward force shear force is positive and downward is negative. Bending moment clockwise bending moments positive, and counterclockwise or anti-clockwise bending moment is negative. So these things you must remember. Okay, and if you same thing, if you take it on the right hand side. Okay, okay, this is from left hand side, this is from right hand side, exact opposite sign convention you can see here. So shear force acting upward is negative and downward is positive from the right hand side. Similarly, the bending moment clockwise is negative, and counterclockwise is positive, just opposite to this. Okay, counterclockwise or anti-clockwise. Now the important points to remember to plot the shear force and bending moment diagrams. Important points to remember. So the nature of the shear force diagram and bending moment diagram for point loads or concentrated loads will be rectangle and triangle. I'll explain what is this rectangular shape and triangular shape while plotting the shear force and bending moment diagrams. The shear force between any 2 point loads remains constant. I'll tell you what is happening while plotting the shear force diagram. The nature of shear force bending moment diagram, shear force diagram and bending moment diagram for UDL will be a triangular shape and parabolic shape. That is, shear force diagram for UDL will be triangular shape and bending moment diagram for UDL will be a parabolic shape. And nature of shear force diagram and bending moment diagram for UBL, that is, shear force diagram will be parabolic and bending moment diagram will be cubic shape for uniformly varying load or triangular load. The bending moment is always zero at the simply supported ends. We can prove it mathematically also while solving problems. I will show it. The shear force and bending moment are maximum at the fixed end of a cantilever beam. Okay, so these two will be always maximum at the fixed end of a cantilever beam. Okay, so cantilever beam is nothing but where one end is fixed, the other end is free. Okay, if both the ends are fixed means conditions different. Okay, we cannot expect that both to be maximum at the fixed end. Okay, it's very important. Make a note. So the bending moment is zero at the tip of a cantilever beam when subjected to a point load or uniformly distributed load. The shear force is zero at the tip of a cantilever beam when subjected to a UDL. The bending moment is maximum where shear force is zero and vice versa for a simply supported beam. Thank you.